So I'm going to talk about what you see on the screen right now. And when I finally finished doing this during lockdown fervor, because this is what you do when you've got time on your hands and you're sitting at home, you come up with nested inference methods. Yeah, so when I submitted this after about a year of work to a journal, they immediately rejected it because they said there's a typo in your title. But there isn't. This is actually what I'm doing. So I'm using transdimensional Gaussian processes by using transdimensional Gaussian processes. So there is an element of recursion over here, and that's what we're doing. So yeah, please don't reject this in your thoughts already. This is not a typo. And this has come about, though I'm responsible for any inaccuracies you see today, none of this work would have been possible without all of these people who I have bothered and battered is a better word, like, what do you think about this? And all their ideas have gotten into this piece of work that you're going to see right now. Okay, next slide, if we are able to get to it. Since this is a bit of a temple of bays, I don't.
It's all right, you're in the right place.
Yes, but I'm sure all of you are very familiar with the paradigm that's being shown over here. I typically like looking at it from right to left. You go somewhere and you turn up with a bunch of beliefs, and then there's the real world, and that's where you bring in your likelihood. And then you balance your beliefs with, or you weight your beliefs with the information you get from the real world, that's likelihood, and you get a reweighted belief, and that's your posterior. So you've got what typically in geophysics is known as a model, M, and we'll get to what that model is in a bit. You've got geophysical data, D, which comes from sensors. Typically, the likelihood is considered to be entirely comprised by random error. And so there's all these statistics you can use to come up with estimates of the likelihood given a model. And then that gives you the posterior belief. And so yeah, so no need to delve further into that. We will get into some aspects of model selection now. So some of you here might be familiar with transdimensional methods or the reversible jump Markov chain Monte Carlo algorithm. And the primary difference between ordinary MCMC and trans-D MCMC is that the number of parameters that you are sampling over is also something that you are sampling over. So you could immediately ask, to those that are not familiar with the reversible jump method, so aren't you over parameterizing, or how do you penalize complexity, and what do you do about having this number of parameters that could just run away from you? So if we have a k parameter model, or what statisticians would call a parameter vector, I guess, given the observed data, then this turns out to be proportional to the likelihood of a k parameter model times this factor over here, which I've bracketed, which in geophysical parlance, and even in the book by McKay on information theory, is known as the Occam factor, this product of F's that you see over here. So what that is, imagine you're doing some kind of tomography experiment in a layered earth. There's k layers, and a priori you're saying that velocities in each layer are uniform and vary between 2 to 5 kilometers a second. And you've got 10 such layers, one underneath the other, underneath the other. Now, after you've conducted your experiment, your inference will surely not say that that's a uniform range of velocities possible, because if that were the case, you've gained no information, right? So it's going to be some fraction in each layer of the velocity space available that you're going to occupy. So that's these fractions F over here. So when you multiply these different fractions into each other, they're very quickly going to tail off. And so you have one factor that's tailing off to 0, and you've got the likelihood of a k parameter model, and you can fit better the more number of parameters k you have. So what you see here is a bit of a balancing act going on. And so this is really nice. It's intrinsic. You can just pull this out of Bayes' theorem. And
so is this the price? So I'm just trying to relate. Yes. So if you've got you're missing an MK on the left side of it, because it's K conditional on D and MK, or just conditional on D?
It's conditional on D.
So the MK then So then the right-hand side is a bit peculiar.
It is a little bit peculiar, but there's some constants that I've taken out.
Yeah, okay. All right, I know, but so we've got a posterior
Yes.
where so K given D is proportional to P of D given K,
Yes.
times P of K, right? And then
It's
now,
not P of K over here. So you can actually, so this is the outcome factor, and it is.
But hang on, so P of K given D is proportional to P of D given K times P of K.
Yes.
So whatever those proportionality factors are, they are in fact representing P of K, because otherwise the equation's not true.
The equation, so what would happen is, irrespective of the value of K, the proportionality constants don't change. So we're sampling over a certain number of K. So,
all right, I'm just saying mathematically that we need to think about that, because that is not P of K.
So I mean, that is so.
So it's it may be that those products of things are in some sense proxying some sort of prior, but they must be proxying some sort of prior, because you have to have a prior on K, and at the moment that doesn't appear.
So whatever the prior on K is, whether it's uniform or whether it's something else like a Jeffreys prior, it will not change for a given range of K. So that's why you can still write this. So it's still constant as long as K is bounded. As long as you're saying that K.
So what about if K is Poisson? I mean, it would be a very different response. So K is Poisson could be the number of things.
So, but the equation here is not dependent on the form of K, it's just dependent on P of K. As long as P of K doesn't change, you're fine to be using this.
Okay, I'm happy with that product being P of K. Okay, that's in fact what it is.
Maybe we'll find out more about this notation as the talk progresses.
You certainly will. So now what's happening here is that if you've got a Gaussian process which you're using to fit a certain function, and that function is this dashed line over here, the dashed black. And if you've got 10 points with a certain length scale, and I think in this case, the length scale was 1/5 of one grid unit. So 0.1 divided by 5, 0.02 or something. And you were trying to fit, given these randomly sampled magenta locations, well, you wouldn't approximate the dashed black line very well. I mean, you can see that you're doing well where you've got a few points, and you're not doing so well in other places. And that's. So those of you who've been working with Bayesian optimization, like, well, given an acquisition function, I should be able to place the magenta points. So I thought, well, if we can do it with an acquisition function for optimization, why can't we use the likelihood to place the points? And you can do something like that, right? And you get a better fit if you had a likelihood, which is based on the misfit, which determines where to place the points. And in fact, this is largely what we do with Tran-STI methods in geophysics anyway. Now, the beauty of being able to use a Gaussian process formulation, I think, is that Gaussian processes don't really care about spatial dimension. So you could have, a 1D process where, your property of interest is changing only one axis. You could have two spatial variables here. You've got an image. So that's actually a milk drop. And that milk drop, it's a low-pass image of the milk drop that is being approximated by approximately 40 Gaussian process nuclei over here. And, I mean, if you squint a little bit, it still does look like a milk drop. And then you could also do the same with about a few nuclei, and you could parameterize something like the Earth's mantle going all the way down to 400 kilometers depth. And again, as Richard will tell you, if you show this to a geophysicist, or well, a geologist actually, they'd begin to draw lines on sections like these and say, oh, well, that's the plume, and that's moho, and that's all kinds of things. And but this is actually just a random realization from a Gaussian prior. But the point is, you can use a Gaussian process, and this is not new to statisticians, but it is new to a lot of earth scientists, that you can use this formulation to be able to parameterize the Earth in 1D, 2D, and 3D. And when you tell people, well, this is actually kriging, then it dawns upon them, oh, this is kriging. So, we can do this, yes. However, there is a catch. Now, I'm showing you here the equation for a Gaussian process mean, and Sally's immediately going to say, why are you using an Euclidean kernel? it's a bad, smooth kernel to be using. And well, it's just a kernel. You can use whatever kernels you like. But what you can see immediately, what strikes you, is that you're going from a large parameter vector, mu star, to a small parameter vector. So for example, in this image, it's a 256 by 256 image, which, if I'm not mistaken, is 65,536, but I'm representing them with just 40 nuclei. So there's just 40 nuclei with some pixel values. And when you construct the Gaussian process mean, you're going from 40 to 65,536. And you're doing that through these kernels. And so in some sense, it's the same as, being able to use splines, or, when you're trying to draw Bezier curves in PowerPoint or wherever, you're actually doing a lot of work by just using a few elements, right? So that has all kinds of pleasing properties mathematically, and parsimony is quite nice, as we'll see.
Is that what's usually referred to as inducing points on the GP?
Perhaps
I believe so, yes.
Yes, then your language.
So these
yes.
are latent parameters that can be placed anywhere that it's convenient in order to give the GP the right shape.
Yes.
So they're not data in that sense.
They're not?
They're not external. They're not something external that's measured, but
No.
they are something that shapes the GP.
Right.
So we would call those inducing points in the sparse GP literature.
Right.
We're just
So
making sure
the
word.
data becomes sort of
Yeah.
like projected into that space.
According to your algorithm, or do you give it some prior set position?
So there is a prior on the locations and the values of these points, but then the placement is determined by the likelihood by Markov chain Monte
So
Carlo.
they move around.
Yes.
Okay.
And it doesn't have to be Markov chain Monte Carlo. You could use an optimization algorithm as well to drive the positions of these things and their values. So it's it's pretty flexible in its conceptualization so far. So now, one of the difficult things about showing this is it's either to a very dedicated statistician audience, or it's to very dedicated, earth scientists. So I never know how to, balance the two. So I have to flip this now, because if you show this with the z-axis going down, this will immediately begin to look like, something that the earth scientists can recognize. Oh, that's the Mohorovic discontinuity, and that's an increase in velocities, or that's an increase in conductivity or something. And actually, if we were to do an experiment, and this is in the Antarctic, a really beautiful experiment in the Taylor Glacier area, Blood Falls, where they've got this hypersaline channel. This is a log of ohm meters, so log of resistivity sensed in the earth from an airborne electromagnetic transient response. So this is the D, and these are the various M's given the data. And so this is the data. That's what you see with these blue arrow bars, and these are the transient responses from various posterior models that have fit the data. And so this came as a bit of a surprise to people, because there's these briny channels within what was thought to be monolithic permafrost glaciers. And not only that, we see tantalizing hints of a second briny channel as well. And it might not be a briny channel, but there's a deeper conductor over here. And I have no idea what this means, but the skeptic glaciologist is very excited. So you can totally use a statistical idea through what you've just referred to as inducing points to control the parameterization for a geophysical model, which really is the full dimensional. So in this case, there's, I think, 60 layers, but I've never needed more than 20 inducing points. So it's a 60-layer model that's been controlled by 20 parameters. And so then you could ask, and this was one of the questions that was asked when I tried to submit this paper, which has been accepted now, why only use the Gaussian process mean? So one of the reasons is you don't need realizations from this large n by n GP covariance, right? Because over here, I just showed you a bit of a simple example with 1D physics, but you could easily have models that have 256 by 256 parameters, or hundreds of thousands of parameters. And in that case, as we know, getting realizations from a large covariance matrix is difficult, or can be challenging. But in this case, because R, so if you go back to this equation, R is much smaller than N, you only need, you can do a Cholesky decomposition to get, to multiply these products. And you only ever need a small decomposition of an R by R matrix. And that's orders of magnitude smaller than, the full N that you might need to be able to model the physics. So there are methods to deal with this using stochastic PDEs that I don't know very much about, but you don't need to use Crank-Nicolson to be able to get these realizations. And in addition, you have the advantage of parsimony. So, which really is a very nice property. For example, Neil has shown in his, I think it was the paper on Hamiltonian Monte Carlo, that even for an independent 100-dimensional Gaussian, it's not very easy to get sampling of just a simple 100-dimensional Gaussian. And so, but when you use parsimony, you're getting help, right? As in things aren't independent.
So can we just go back? How does why is the Crank-Nicolson? So the Crank-Nicolson, is sort of makes things scale well so why is it not necessary here? What is it about this particular setup that makes it this sampler able to propose and accept, have a high, what you're saying is you have a high acceptance. You're talking here about the sampling scheme?
I haven't shown that yet, but yes.
But is that what the Crank-Nicolson is used for?
It's not using Crank-Nicolson.
No, I know.
Yes.
But does that line refer to the sampling scheme?
It does, because you could use Crank-Nicolson, but you'd still be using a high-dimensional. You'd still have a high-dimensional model space to populate, right?
Yep.
And there's no getting away from that.
Yep.
Whereas with parsimony, you don't really have to worry about that, but you still have to go from that low dimension to that high dimension. And
okay, so you're saying that you don't need the Crank-Nicolson because you've actually reduced the dimensionality so that it's not high dimension. Gotcha.
Yes.
Right.
But I mean, you still have to go from the low dimension to the high dimension and compute the kernel matrices. And so, as usual, you're being extremely perceptive, and you're seeing where I'm leading to. But
no, I'm just not. Just done it for a long time.
So what you're doing here is, here's the high dimensional matrix, which can be, if you're putting your model physics into a finite element modeler or a finite difference modeler, this thing here, say you want to, solve the wave equation, or you want to solve the elastic body wave equation, or I don't know, geostrophic flow or something, some Navier-Stokes, this stuff over here, these are the parameters that are high dimensional, anywhere between hundreds to tens of thousands of parameters. And you've got these two kernels, which need to be computed and multiplied into this low dimensional model vector over here. So that's how you go from low dimension to high dimension. Now, you could do this. So you immediately see that if this was, say, 100,000 by 1,000, that would be a lot of computation to do every time there's a model update. Right? So, however, if you pre-allocate the maximum size of these matrices, and you do something clever, and you notice that I'm just going to use something very simple, like just Metropolis Hastings, for example, and I'm going to, just perturb one parameter at a time. You can then decide, I'm going to swap only the relevant rows and columns and compute the Euclidean distances for the kernel computation in only the relevant rows and columns pertaining to the Lth parameter that I've perturbed. And this is a huge time saving, because I don't need to recompute or reconstruct either of the two, these huge kernel matrices, to be able to go from my low dimensional model when I'm updating to get the updated high dimensional model.
But how this is the inverse of the matrix, right? So it's all connected with the inverse.
Yes, but you can still do this. So you would never explicitly compute the inverse, right? You'd solve because it's symmetric, this one, right? So this comes from a self kernel where every inducing point is interacting with every other inducing point, so it's symmetric. So you can then use Cholesky, and that just makes it really fast.
So you don't change.
So it's only R by R, that one. It's not N by N, the inverse.
But still, we should change the parameter. So which parameter are you changing?
So so say for example, an inducing point over here could be you know, velocity within the Earth, or it could be density within the Earth, or it could be electromagnetic conductivity within the Earth. So I'm saying I've got 40 parameters within a three-dimensional volume, 40 inducing points, and it could, this L is anywhere between 1 and 40.
Do you change the hyperparameters of the kernel itself?
We're getting there. We're getting there. Oh, you guys are too sharp. Yes. So in this case, you have to be a little bit judicious about your choice of how you think the Earth is. You know, what are the correlation length scales within the Earth? So you don't change that.
Okay.
Another way to make this fast, perhaps, is you can use Hodler. Everybody was talking about this a few years ago. You've probably heard of it. Hierarchical, off-diagonal, low-rank approximations to. So it's some way of, if you've got really sparse, or if you can prove that your, you know, covariance matrices are low-rank, then there are nice methods for inverting them. So yeah, so I saw this somewhere. But in our case, this is a small R by R matrix, so we don't need to do that.
Yes, that's the point. Yeah, just
Yeah.
But we haven't yet come to the transdimensional stuff, right?
Um,
Or is this?
You have actually, because this vector M
Yep.
can grow. So this vector M is pre-allocated to a maximum size. These kernels are pre-allocated to a maximum size. And so if I want to remove, if I do depth to a certain parameter, I'll just move this right to the end. I'll just move that right to the end. I'll just move that right to the end. And I'll move this right to the end. And I will just multiply a smaller system.
Okay, but so what about with the birth? I mean, so you basically, what you're saying is you keep all of these things and you reshuffle things in order to make it computationally feasible. But you know, normally when you sort of have reversible jump and you're going to propose that you give a birth to a new component,
Yes.
you need to, you know, it's hard to come up with good proposals that have a high high acceptance rate.
Yes.
And so you know, typically what you do is connect it to the current value in the chain, and you add some noise. I mean, Hattie's been working on some papers about this. So how do you do that there? How do you make is that the technique you use, or do you use another technique to actually propose a whole new set of parameters?
So
how do you connect them to where the chain is?
So here we've done things that are a little bit experimental. So there's Stan Dosso at the University of UVic, Victoria in Canada. And he's experimented with focus proposals where you say, well, I'll just take the average. If you had two layers of a layer above and below, I'll take the average and I'll propose a small perturbation from the average of the two. And or you can look at just proposing from the prior. And I know for a fact that proposing from the prior maintains detailed balance, but it might not be the most efficient.
No.
Whereas
it'll be very inefficient.
Whereas if you propose from using a focus proposal, sometimes depending on how large your proposal width is, you're again not maintaining detailed balance. And
well, you will maintain detailed balance because that's in the acceptance probability of Metropolis Hastings. That's why you have it, to maintain detailed balance.
That's what it would seem like, but it's not obvious. But I've actually reviewed some papers where they've shown what happens to detailed balance when the perturbation steps are too large. When you're using a Gaussian proposal to step away from, and just break a cell into two or give birth or do whatever, a very large proposal width actually breaks detailed balance. So I'm not answering your question.
No, it won't. It won't.
Should not.
Yes, it doesn't. Yeah. What it means is that if you use a standard acceptance probability and you don't compute the right acceptance probability, it will break. But it will not break because of the distance in the proposal. I can assure you 100%.
So maybe, they weren't, maybe the acceptance probability wasn't the right one.
Yeah, that's the point of the acceptance probability, is to make detailed balance hold no matter what the proposal. That's the point.
It's true. So what I've done over here is I've just used, I have the option of using focus proposals, or I have the option of using proposals from the prior. And if I get within 10%, I'm happy. You know, 10% might sound like it's very low, but you know, I seem to be able to converge within a number of
10%
iterations.
fine. But that's a different thing from
Yes.
violating detail balance.
That is true. So I'm not really answering your question because I don't really know what efficient methods are for giving birth. So that is an open area where I think, you know, if you could.
Well, there are standard methods out there, but yes, so certainly your current area of research, Hattie's looking into sort of bits and pieces, things to do with that. Yeah.
Sounds like a good thing to go offline about tomorrow.
No, that's a really
Or
good.
tonight over a beer. I don't know.
Sure. Yeah.
Okay.
So here's now, so again, the geophysicists will say, well, all that's great, but what can you do with it? So here's a two-dimensional problem, which had, I think, some 40,000 cells. And this is the imaging of, so what you can see here is a magnetotelluric problem. And this is from my advisor's PhD. So he had this data and he inverted it using a deterministic method. But we wanted to find the uncertainties on it. And it's an electromagnetic problem where you're sensitive to conductors because it's an inductive problem. So you need something to induce currents in. Now the salt over here, which is geologically deposited in the earth over millions of years, I'm not a geologist, don't ask me. The salt is extremely resistive, but the sediments in a marine environment are quite conducting. So you want to image the salt, but you can't because it's resistive. So you're trying to image the shadows of what you can see. So you pretty much have very low uncertainty. This is the interquartile range you see over here, or interquartile range in the log resistivity space. There's not a whole lot of uncertainty with the sediments, but there is quite a lot of uncertainty with the salt, which is what you're interested in. But you can still see the edges of the sediments. And so for those of you who are familiar with hydrocarbon exploration, very often structures like this will hide hydrocarbons underneath. So this is why various people are interested in this kind of uncertainty estimation of where the salt lies. And you can see that when you're close to the surface, you depending on, we cut out some of the high frequencies, which is what is responsive to the near surface. And so we see that some of the near surface stuff is also pretty uncertain because we cut out the high frequencies. But the point is, you can do uncertainty estimation for large problems using this methodology. You can go from 1D to 2D, and it's not a problem because the theory doesn't care. Never believe that an image makes any sense unless you can see the data fits. So for magnetotellurics, here's apparent resistivity and phase, which is what you're fitting at some 7 or 8 sites. Now we get to a point where you say, well, that's great. All the variations you've shown have been smooth, but what about a function like this? When I showed this to my wife, she's a neuroscientist, a neuropsychologist to be specific, and she said, well, that looks like activation potential for nerves in the brain. Like, okay. And it turns out that statisticians and neuroscientists have been studying these kinds of models for a really long time. And so this is actually in Christopher Pachurek, I think that's how you pronounce his name. It's from his PhD thesis. He's worked on some methods to be able to use non-stationary Gaussian processes to be able to model such functions. And then Lagemann et al. Done some stuff a little bit later. And I thought this was a good test example to do a regression example. And this is actually now data. So there's no geophysics here anymore. So this is a regression problem. You want to, there's 50 data points here. You want to find out what's going on at 100. And so you can do probabilistic regression using just non-nested, simple trans-dimensional Gaussian processes where you're placing the nuclei and then figuring out the mean of the Gaussian process. You're doing that a whole number of times and you're marginalizing, and what you're seeing are the uncertainties over here. Darker colors correspond to high uncertainty and brighter colors correspond to high certainty. And you can see that even with a fixed length scale, you haven't done too badly, which is surprising, right? Because how are you with a fixed length scale able to deal with this sharp discontinuity?
Depth spec something like, yeah.
Yes, yeah.
Right? And this is because of the trans-dimensional nature of things. And it's what I really like about the trans-T method. And you can,
Sorry, so you're basically bombarded with more inducing points around the edge, the sharp edges. That's what you mean?
no, you aren't really, because they just decide to, they just line up and move wherever it's necessary. Yeah,
Okay.
because I mean, it's part of the parameterization.
Okay.
To be clear, I guess what we were showing us was the posterior mean of the realizations from the GPs that fit those data, right?
And there's a whole lot of means here,
Mhm.
because each mean represents one model.
Right. So the point is, if you took a draw from,
Yes.
it wouldn't necessarily look like that.
No, but in this case, you can see the 5 and 95% quantiles,
Mhm.
and they're really narrow. So in this case, in this particular case, they would look like that,
Mhm.
but not necessarily, where the quantiles are wider.
Mhm.
Yeah. And however, so the number of nuclei required, and it's, there were 100. So the grid was actually 100. So if you go from 0 to 1 over here, there's actually 100 divisions in that grid. But I've only ever needed something like 15 samples. So it is parsimonious, by a factor of about 5 or so or better. However, because this is a synthetic example and I know what the noise is, I can see that I'm not quite getting to the noise level, and different colors are because I'm using parallel tempering, and the darker color is the target chain. I'm not quite getting to the noise level. So I'm doing well. As a geophysicist, I'd probably accept this kind of model. But
So the noise level is the noise level of what?
so there is a perfect function, and I have
So
some.
y is equal to f of x plus e, and that's
Yes.
the noise of the e.
That's the E.
Okay. Good.
So I should be able to get down to the E, or at
Yeah.
least the chi-square of the E.
Yeah.
But I'm not able to. Not by a whole lot, because this is
And the e was, the sigma squared of the e was 50. That's how you generated the data. Is that your concern in this? You're not recovering what you generated from?
yes.
I understand it?
Yes.
Yeah.
So I should. So I'm showing you chi-square over 2 over here, and I should be getting 100, but I'm not. And so chi-square over 2 is 50, but I'm not quite getting that.
Right. Okay.
It's not bad.
No,
It's not bad, but
Yeah, but it never even gets down there, which is a bit of a concern.
it is a bit of a concern.
Yeah.
Now, if
So what does that say about the model?
it means it's you need more complexity.
Okay.
But you were saying, was someone saying something?
No.
So basically, you overestimated the process noise.
No, there's no way in which the model can get to the process noise, because it doesn't have flexibility enough. It's just you can think of it as, dare I say the word, regularization.
Mhm.
It's just not going to get down there. It's just if had I used a smaller correlation length, it might have.
Okay.
So then what I did was, what if I said, let's have a second nested Gaussian process, which is able to change the length scales used. So basically another Gaussian process, which is now parameterizing the hyperparameters. In which case, in this case, I'm letting the nugget be fixed. So it's only the length scales. And so that's the difference between.
So you directly model the hyperparameters as a function of the covariance.
So there's another prior on the hyperparameters.
Yeah, and you make
That's
the
another
hyper,
GP.
you put a GP over that.
I put a
Yeah.
trans-dimensional GP as well.
Yeah.
So it's trans-dimensional GP and trans-dimensional GP. And so what happens then, and so this is from Pacherek and Skirvish, where at the ith and jth locations, if you've got an interaction between the ith and jth positions, then the kernel has to be modified using, this root over qij is just root over quadratic distance. R is any kernel function, return. I personally like the return 3 over 2 because it seems to be a nice trade-off between sharpness and smoothness. And notice that if I is equal to j, it just goes back to the stationary case. So this is a really nice, I think, a very simple but very deep modification in Skirvish's.
Well, if I goes to J, what you've got is the variance. But
No, the values of I and j. If Ci was equal to Cj.
So CI, not YI.
Yes. No, you're right.
Okay,
You're right.
okay.
If Ci was equal to Cj, yes,
Okay.
yes, absolutely. I and j are the positions of the two interacting points in space. So this is, now this kind of messes with your head the first time you see it. Probably not, because I think you're already on to me over here, except that I'm doing a trans-dimensional version of what you're thinking. So if I've got length scale values in their locations within one trans-dimensional parameter vector, that's theta s, this can give you a mean, which is mu s. Now, this mu s is now a vector of length scales. And I can feed this into another Gaussian process, which is non-stationary now. And it'll use that spatially varying length scale, mu star s, with a fixed nugget. And then that'll populate the model vector with the discontinuities more accurately, is what I believe. But however, there is a catch here. To compute the likelihood doesn't know anything about length scales. So you've got to compute the function, the f of x. And but to compute f of x, which is going to be given by mu star non-stationary, you've got to compute mu star stationary. So how do you do this? And this is where, instead of using Crank-Nicholson, I've just said, not all parts of mu star s. So not all parts. So if I make a change in only, so for example, I have it color coded here. So if I had selected in the stationary Gaussian process one nucleus, and I've perturbed the value of that, say, it's going to change the the mu star s, which extends in this entire blue domain. I haven't shown it to you because we'll just go crazy then. But it's only going to impact the update if you've used Metropolis Hastings to change, say, the length scale value here. The perturbation will be felt most strongly close to within a few length scales of the stationary nucleus over here. So then I'm going to do a KD tree search to see in the non-stationary Gaussian process, which are the nuclei that are falling within that radius. And if they are within that radius, only do the kernel computations, which you saw here, just modify the L's that fall within the radius of the change. And so it's kind of a neat approximation. And this completely obviates the need to recompute the entire kernel matrix. And what does this do? So now, this is your second, the whole ensemble of means from the second Gaussian process. So this is coming from the stationary Gaussian process. This is the non-stationary Gaussian process. The stationary Gaussian process gives you a spatially varying length scale, or a whole bunch of spatially varying length scales, which then get fed into the non-stationary Gaussian process.
So you've got a non-stationary Gaussian process over the function, which is, and then the parameter which controls that the parameters which control that non-stationary process are themselves put a non-stationary process over those parameters. Is that correct?
Oh, I could
stationary.
I could go to another level of.
So okay, that's
yes.
The second one is stationary.
Yes.
Right.
But
okay.
you could put in a third one.
Yeah, well, I don't know if you need it. I think it would only
Right,
fit,
right.
quite frankly.
Exactly. Then it would be turtles all the way down. But I don't think you need to, though. But that's exactly right. So I think if you have a stationary one here with small enough length scale such that it can represent sharp changes, then you're fine. And there is one problem here, which
you have
is
the changing dimension on it. So you have the changing dimension on both of the
Yes.
function and the
Yes.
and the stationary.
yes.
So you're saying that the function itself is changing dimension, and then the processes which describe that function is also
Yes.
are they changing dimension in response to the changing dimension of the function, or are they changing dimension just in and of themselves?
So they are like.
So I'm just a bit confused.
It is
Sorry.
a little bit confusing because they're nested and recursive, right? So they are a little bit confusing. And well, so what they're doing is they're responding to the change in the function. So over here, you can see that there's a kink.
Yeah, I can see that.
So wherever there's a kink, and wherever there isn't one, it's saying, you know what, the length scales could be you're basically going back to the mean. You're not very sensitive
Mhm.
to the length scales anywhere except at the change, because there's no physics over here. There's really nothing. It's a regression problem.
But that would then sort of say that the non-stationary component, you know, of the smoothing parameter is mapping onto the non-stationary component of the function. I'm just trying to figure out why you need those different
Because-
varying dimensions. Sorry, the varying dimensions on the function and on the non-stationary and on the smoothing parameter. That's okay.
Because again, the same arguments of parsimony apply to even the length scale parameters, right? Because if I had to populate a length scale parameter vector, which is, so the length scale, so over here, mu star S and mu star NS, what are we looking at? So this mu star S in red and mu star NS in black are basically, this is mu star S, or a whole ensemble of stationary length scale means. And this is a whole ensemble of non-stationary function approximation means. So they still have to map onto a 100, in this case, I think I've got 100 or 200 cell grid vertically. And so, you know, the arguments of parsimony, which work in favor of the function approximation, also work in favor of the length scale approximation.
Yeah, I wasn't really worried about husband, but that's good.
Oh, no? Well, I am, because how do you populate a 200
No,
dimensional
I just
grid
mean that it
otherwise?
was just not, I was more worried about why the changing dimensions and how they related to each other. You've got
But
them at
changing
two
dimensions,
levels.
the argument is again like parsimony, because I don't know of any way to, unless I enforce parsimony, and I don't know the level of parsimony, which is why I defer to the reversible jump, right?
Are you just trying to capture jumps?
Pardon me? Am I trying to attempt
Capture jumps in the function?
two jumps in a function?
Are you trying to capture? So he's trying to do what we would say is locally adaptive regression by the look of it.
So basically, we did that, you know, Stats has done that by doing a Gaussian process for the mean and then a Gaussian process for the log variance or things like that. You're doing it somewhat differently, right?
Yes, and so you know,
Is this multi-dimensional, one dimension?
this is multi-dimensional.
Okay, but what if you did the same thing, you know, in multi-dimensions? You had one Gaussian process for, and it's not just jumps, it's differences in just the curvature. What if you did a Gaussian process for the mean and a Gaussian process for the log variance? Would that work?
It's possible. When you say the log variance, you mean the log variance of the Gaussian process itself.
Now, I modeled the log of the variance of it's a function plus noise, and I modeled the log of the variance as a Gaussian process.
So I suspect you could do these things, but when you do, you'll still end up with a Gaussian approximation, and that tends to be, well, unimodal, right? And some of our geophysics problems are so horribly nonlinear that you're going to get multimodality. But maybe
I'm not gonna argue with you, because I'm here to actually drink coffee and learn. But so I missed the first part of the talk, but from the few words I missed a bit of the talk, so I'll just learn from what you're saying.
No, I'm happy to continue this discussion.
No, move on.
So, but wait, quick question. So
Yes,
you're
yes.
still placing the GP on the log of the length scale, right?
Yes.
It's always possible.
Because it has to be positive. So I could perhaps have like an arctan or something like that to enforce things, but I think that'll just ride me up against the edges. I don't know. That's a very good question. So which is why I had to do log, because yeah, there are probably other ways to do it as well. But yeah, I decided on log. And also in geophysics, very often length scales can vary by orders of magnitude. So it seemed like, you know, a sensible thing to do. But that's a very good
And
point.
this is inspired, I guess, in the
Well, which is what Robert's
heterostochastic.
point about the log of the variance. That's why you put the GP of the log of the variance, because to make it positive, yeah.
Yes.
Yeah.
Yes.
And I guess you're aware of heteroscedastic GPs, where they essentially put a GP, but then on the noise
Yes.
variance.
That's what
So-
Robert was talking
So you
about.
could, oh, I see, yes. So you could certainly do that as well. So are you able to model non-stationary processes better with the noise or with a length scale? With both, you know, I don't have the answer to that. So if you zoom in, you'll see that if you'd use a stationary Gaussian process, as opposed to a non-stationary Gaussian process, well, you know, the true function is shown to you with the white dashed line. The 5 and 95% quantiles are shown with the dashed green. So you can see that clearly this is, well, not clearly, but it is doing better, the non-stationary Gaussian process. And that's because, well, the length scales are allowed to change over here, and they're changing by themselves. And not only that, it fits the data. I haven't shown that to you over here, but it actually gets to the right chi-square. Now, you could do the same with 2 dimensions and multiple channels in your Gaussian process. So you're doing the same thing, locally adaptive regression, but you want to find the uncertainties. And this is what happens when you use a fixed length scale. And it's not bad. It fits the data to within noise. It's the epsilon that you were talking about, Sally. But if you used a non-stationary kernel as well, so you used the recursive method that I just told you about, well, then you can calculate the, what is this again? The something scale. It's the fidelity of your compression, essentially. Higher values are better. And if you've got, if your compression, this is from the image processing literature, and it's computed in dB. If you've got, if your reproduction is as good as the original, then essentially your PSNR is infinite. So you can see that the non-stationary version of the algorithm performs better, and this is just the mean model. I can also show you, statistics, on the pixel value, on the log of the length scales in X, the log of the length scales in Y, and these are the median values of the image, of the length scales in X, of the length scales in Y, and this is taking a profile and showing you the actual histograms on the length scales. Again, automatic adaptation to the data, and as you would expect, where you've got edges, the length scales become smaller, and where things are more or less constant, the length scales tend to be larger. So it's kind of nice. Lastly, I'll leave you with an example from the control source electromagnetic, another geophysical Australian example, Scarborough gas field, sorry, in the Northwest Australian shelf. And you've got what my friend and collaborator David Meyer called the rabbit ears, which mark the 50% gas saturation line. So anything within this is hydrocarbons, anything outside is not, or not commercially viable. And this is a resistivity profile within the Earth, and it's a bit of a shame and a bit of a good technology demonstrator, because these siltstones over here, from what I understand, is that they're quite resistive. And a hydrocarbon reservoir is also resistive. So you've got these 2 resistors which are really close to each other, and you're trying to detect them with an electromagnetic method. So can you tease them apart? And what you'll see is that, so on the right over here are the real and imaginary components of the data, and the data are given in color. And you've got also, I think, 500 different model fits, which fall well within where the data are, or 2 standard deviations, both for stationary and non-stationary.
Can you blow that up, or was it, no, that's just, what do the different colors refer to?
Each color is a different frequency of acquisition.
Right.
So you've got,
And which one is the data then?
the data, so there's 50 transient response, not transient, this is in the frequency domain. So you've got, you've got the ship at 0, where you got a transmitter, and you've got receivers at all of these locations given on the x-axis. So wherever you've got data, you've got a receiver lying on the seafloor.
Right. Okay, right.
So this is frequency domain data. So you can see waveguiding in this, perhaps. You can see notches, right? So yeah, so though this is really low frequency, it's 0.25 hertz, because if you had any higher frequencies in salt water, you just totally attenuate. And so it's very close to the sea surface, which is why the waveguide goes preferentially through the sea floor as opposed to the water, because it can't go through the water, right? I mean, it does, but it's not that much. So the data fits in both cases are about the same. However, well, look at that. The stationary posterior distributions of resistivity show you, well, you do see something between 1500 to 1700 meters, which is reminiscent of something resistive, and at about 2 kilometers, there's something even more resistive, but I try to capture a sharp change, so I'd used a very small length scale. It's kind of made it very spiky and noisy, whereas if I had let the adaptation be automatic, it figures out, look, there's something going on at 1500 meters, and then there's something else which is quite reservoir-like at 2 kilometers, and so this is just a better approximation. And then you can zoom in, and you'll see that one has basically missed everything besides the sharp change, because because there's something going on with the sedimentation over here. It's very gradual, so there's not a sharp electrical resistivity contrast at the top, but there is at the bottom. But in this case, it's just able to adapt to the geology and basically the electrical contrasts, resistivity contrasts better. And so, you know, to leave it at that, this is, whether you use the nested version or you use the non-nested version, it's a generic inference methodology. When there's significant non-stationarity in the length scales, you can nest them, and I think 2 levels are fine. And this is a message to, you know, geophysicists, but really to any people doing inference or machine learning, that the trick is, if you want to learn about something, you might need to learn about that thing as well. And in some senses, it's not surprising, because one of the first things they teach you in undergrad physics, and physicists will swear by this till the end of their days, and I'm sure most, you know, mathematically inclined people will, Taylor series approximations, right? You can think of the first level as being the constant, and the second level as being the gradient term. And were you asking a question?
No, sorry, sorry.
Sorry. So yeah, so you can think of it as Taylor series approximation. So the length scales can be thought of as the inverse of the you know, the gradient or the functional gradient at any point. And so yeah, and then you also have to propagate this back up. And this is where things get a little bit nasty, and that's why you had that diagram that I showed you, which was a little bit confusing, but when you read the paper, hopefully it makes more sense than my babbling about it. So you kind of have to propagate the changes back up from the stationary to the non-stationary model. And that requires a little bit of thinking. But yes, as in it's explained in some detail in the paper. So yeah, you can read all about it in this paper there. And yeah. So if there are any further questions, I'm more than happy to take them.
Thank you very much.
Thank you very much.